The next topic in Unit 3 is points of inflection. So if we look at this image to the right, we already talked about relative extrema, which here in this picture we have two relative minimum and then also a relative maximum. But what we also talked about before was concavity and how rate of change can form concavity. So on the left side of this, the function is concave up, which means the rate of change is increasing, which is causing that concavity to be facing upwards. But on the other side, we also have concave up, so the rate of change is also increasing within that part. But in the middle, we have concave down, which means the rate of change is decreasing. Now, just like we have relative extrema, the slope here is negative, and then it changes to being positive, changes to negative again, and so on and so forth. A function changes between increasing to decreasing, which is why we see relative maximums, and when it changes from decreasing to increasing, we see relative minimum. The same has to happen in order to change concavity. At some point, a single point, the rate of change is changing from increasing to decreasing and decreasing to increasing. And those points are called points of inflection. So a point of inflection is a point of inflection, and it's a point that occurs when a function changes from concave up to concave down, aka the rate of change changes from increasing to decreasing, or vice versa. And if you haven't heard of vice versa, that just means the other way it will also occur. So it's when a function changes from concave up to concave, that should say down, to concave down, sorry about that. Which also means the function is, the rate of change of the function is changing from increasing to decreasing, or vice versa. I am messing up all the grammar today, to decreasing, or vice versa. Okay, and the same can be said for the other way, when it changes from concave down to concave up, or the rate of change changes from decreasing to increasing. So when this happens, we have a point of inflection. And if we look at the image here, this has pretty nice, well, it has perfect vertical symmetry. If we look at where the concavity is occurring, it's concave up here, and then at this point, it changes to concave down, all right? And then again, it changes back to concave up. So if we look at the points at x equals -1, those are our points of inflection. That is where the concavity is changing, and that is where the rate of change is changing from increasing to decreasing, and then decreasing to increasing. So we're going to have those points of inflections at x equals -1 and x equals +1, which is part A of number 9. All right, for each of the following intervals, determine if the rate of change of g is increasing or decreasing. Explain your reasoning for each answer using features of the graph. So questions like this can sometimes confuse people because you have to make sure, are we talking about the function increasing or decreasing, or the rate of change increasing or decreasing? If you see rate of change, that means you need to look at concavity. If you just see is g increasing or decreasing, you look at whether the slope is positive or negative, okay? So we're looking at the interval from 3 to 4. So from 3 to 4, I'm going here. So yes, the function is increasing, but that's not what it's asking. It's asking, is the rate of change increasing, or is the rate of change decreasing? And we can see that this interval is part of the function when it is concave up. And that's happening because the rate of change is increasing, okay? So the rate of change, and I'm going to abbreviate just because I didn't leave a lot of space for this. I don't usually like abbreviating. So the rate of change is increasing because g of x is concave up. And these justifications are interchangeable. Justify that it's concave up on this interval. Well, the rate of change is increasing. Justify that the rate of change is increasing. Well, the function is concave up. So these are interchangeable, and depending on what you're being asked, you can use the other to justify one. Now we're going to look at from -4 to -3. So we're at -4, we're going to -3, and you want to read the graphs left to right, okay? We're traveling through, you can think of x as time. I know we're in negative time right now, but you want to think of reading these from left to right. So from here, the function is decreasing, but it's part of where the curve is concave up. So therefore, the rate of change is increasing because g of x is concave up. The exact same justification for letter I. And again, abbreviating because I don't have a lot of room. But try to refrain from abbreviating, always writing complete sentences. The next segment is -1 to +1. So we already talked about these being the points of inflection because that's where the concavity is changing. If we look from -1 to +1, now the function it's increasing, but then it's decreasing, okay? Which means we are going through a relative maximum, which means the function will be concave down here. So from -1 to +1, the rate of change is decreasing because g of x is concave down. And the last one, we want to look at 1 to 2. So from 1 to 2, the function is decreasing, but the rate of change is increasing because this part of the curve is concave up. So the rate of change is increasing. Sorry, my dog. Because g of x is concave up. All right, this last problem, I placed it here because you don't want to get set in one mindset. You have to be able to jump from, is the function increasing or is the rate of change increasing? And you have to be able to pull the information from a particular problem. So example 10 does require a calculator. So for 0 to 3, the number of cars in a parking lot at time t hours can be modeled by the function c of t. Based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing? So the question isn't asking when is the rate of change changing. It's asking just in the parking lot, when is the function changing from increasing to decreasing, aka when is the slope changing from positive to negative. So we're looking for a maximum. Okay, so I'm going to go ahead and type this in my calculator, and we're going to find the maximum. If you see a function like with all these decimals, you're not going to be expected to factor that by hand. You're going to be expected to use a graphing utility and know how to use it. So in class, we always use the TI-84. You have the option to have Desmos out. We will never use it on an assessment in the class, but you do get a very restricted version on the AP exam, which as we get closer to the AP exam, like in March, April, May, we'll start using Desmos more. But for now, we are using the calculator. You get both. You get a calculator and you get the Desmos. So you will have access to both. So in the calculator, I'm going to locate mine. Uploading videos for YouTube. Okay, so the function is negative 1.37. It says t, but we're going to put x to the 5th, plus 4.218, x to the 4th, and then minus 0.357, x squared, and then plus 3. And the problem specifically said from 0 to 3, so I'm going to go to my window. I'll do -1 just so I can see beyond the bounds a little bit, and +4. And then for the y values, I'm going to do zoom 0. That way I'm not playing around with the window too much. Now, obviously, this is an application problem. I don't care about what's happening unless it's in quadrant 1. So I'm going to fix my window and then make my y min 0. Because when you do zoom fit or zoom 0, it tries to fit all the extrema, but then if it's going to like -infinity, it'll try to fit all of those values in there too. And then now we have a comfortable window to work with our maximum. So this particular problem said, based on the model, at what time t does the number of cars in the parking lot change from increasing to decreasing? And we can see that that maximum is occurring between 2 and 3, okay? But you don't want to guess. You don't want to use the trace and just move back and forth and try to get as close to that decimal as possible. You need an approximation that is to 3 decimal places that is as accurate as possible. So we'll do second trace. We're going to go to maximum. And I know it's between 2 and 3, so you can use the left and right if you want to, like we did before, but I'm going to hit 2 and then 3. And then guess if you want, and there we have it. So we have the maximum occurring after 2.445 hours, but it's, oh, that's what it's asking for. It's not asking for how many cars are in there at the maximum, it's asking when does it happen. Okay, so we need that x value there. Okay, so a quick sketch of what we saw looks something like this. So here we had 2.445. And it was 31.897. Yes, that's weird, it's a decimal, but we don't have to worry about that because the problem is not asking for that. So on the left side of this, the function is increasing, and then on the right side, it is decreasing, which means we found our t. So at time t equals 2.445 hours. So I know in the calculator, we used x, but the context of the problem is using t. Follow the variables that you are being provided with, okay? The number of cars in the parking lot changes from increasing to decreasing because there is a maximum at time t. That looks terrible. Time t equals 2.445 hours. And if you're like, how do you know what to say? Well, go back to the question and just repeat what they're telling you. You're justifying the the number of cars in the parking lot changing from increasing to decreasing. So I literally just copied and pasted it to justify that. And my reasoning is because there is a maximum there. So just like with concavity, we talked about the rate of change increasing because it's concave up or vice versa. We can do the same for increasing for a function that is increasing to decreasing. It's because there's a relative maximum. And then if you have to justify a relative maximum, you state that, well, the function is going from increasing to decreasing at that point. Therefore, it's a maximum. So they work both ways, and that's how you justify one using the other. And then same thing if you were like, what's the minimum? Or you would justify saying the function is going from decreasing to increasing. Okay, and a lot of that is going to happen in this course. It's kind of feels like you're running in circles, but that's the point. You want to understand how the rate of change is affecting a function, and how the rate of change is changing is also affecting its concavity. Okay, all right, hope this helped.